Welcome to qnawire.
Hi, so for this problem we have two different possible insoluble solids. The first one it is going to be barium sulfate, which solubility product constant is 1.07 times 10 to the minus 10. And the other one it is going to be the silver version of that sulfate, Ag2SO4, which has a constant of 1.2 times 10 to the minus 5. So first of all, we need to know which one is going to react first. For that, let's remember that the solubility product constant for both of these species is going to be based on the corresponding equations. So this is going to be a pure solid, and the K of solubility product, it is going to be the concentration of barium 2 plus for this compound times the concentration of SO4 2 minus. In the case for silver, this is going to be 2 times the concentration of silver 2 plus, of silver plus sulfate. Both of them in aqueous medium. And let me just put the plus a little bit more in the center just to make it look a little bit prettier. So in this case, the K of solubility product will be concentration of Ag plus squared times the concentration of SO4 2 minus. Okay? So first of all, by looking at the solubility product constants, what we would expect is that in both scenarios, the amount the amount that is going to end up in the case for barium, it is going to be much smaller because we know that that constant is equal to 1 times 10 to the minus 10. But in this case, we need to consider that one of the products does not have a one-to-one relationship. So if we were to have a nice table for both of these equations, we start with the solid. I'm going to write it down as the sulfate, ion plus sulfate. So this one is the solid. What is going to happen is that at the beginning we have 0, then the change is that a certain amount is going to be dissolved. Sometimes you can use S just to make evident that that is the solubility. And at the equilibrium, we're going to have S and S in the case that we have a one-to-one relationship. Now, for the case of silver, what is going to happen is that this becomes 2S and 2S. So the result changes a little bit. Replacing those values for barium sulfate, that solubility product constant, it is going to be S times S. So directly S squared. And for the case of silver sulfate, this is going to be 2S squared times S, which becomes 4S cubed. In order to know what that value of S is going to be, we need to solve this for both of the equations. So for barium sulfate, we mentioned that this was 1.07 times 10 to the minus 10. And for silver sulfate, the value is 1.2 times 10 to the minus 5. Now let's find the corresponding values of S. I'm going to label the first one as S for barium sulfate. And the second one as S for silver sulfate. The results are, in the case of barium sulfate, this is going to be 1.034 times 10 to the minus 5. And in the case for silver sulfate, it is going to be 0.0144. So you can clearly see in here that the solubility for barium sulfate, it is much smaller than the solubility for silver sulfate. That means that barium sulfate is the one that is going to react first. Now, for solving the first question, if sodium sulfate is used to selectively precipitate one of the cations while leaving the other cation in solution, which cation will precipitate first? So the one that is going to precipitate first is the barium sulfate. Next up, what is the minimum concentration of sodium sulfate that will cause that precipitation? In order to know that, we know that for the barium sulfate, in order to have some precipitate, the concentrations of barium 2 plus and of SO4 2 plus 2 minus need to be equal or higher than the value for the solubility that we found. So S and S. Next up, when we have the reaction, in order to get a result of barium 2 plus equal to S, we are going to use the initial concentration of barium 2 plus minus the solubility, the amount that we found that should be available at equilibrium, to know how much reacted. In the case that the concentration of barium is higher than this threshold that we have put, remember that for this type of equation, when Q is lower than K, which is the case when you only have a lot of barium and you're still adding a little bit of sulfates, what is going to happen is that the equilibrium will be tilted towards the right. That means that we need to increase the amount of products. So the solid dissolves. That is why all of the sulfate that you add, it is going to being kept into the solution until we find that threshold. Once we have found the value for Q, which is larger than K, that means that we have more concentration of the products than we have according to the value for K, we are going to have precipitation. So this is why we can use this equation to know how much reacted. In the case of barium 2 plus, our initial concentration, it is going to be 0.015 molar. We are going to subtract the value for S that we found, that is 1.034 times 10 to the minus 5. And this is going to give us 0.01498. And that is the concentration of sulfate that we need to add for precipitation to occur. Okay. Why is that? Because everything that is being added, since the concentration of sulfate, it is still not within the range corresponding for barium 2 plus in order to be able to form the solid. We need to keep adding and adding and adding more until we reach something close to the stoichiometric relationship of barium 2 plus. Okay, so next up is what is the remaining concentration of the cation that precipitates first after the second ion just starts to precipitate. In order to know that, let's assume that we have already solved the value for S for Ag2SO4, right? And we found that that solubility coming from this equation is 1.2 times 10. Sorry, it's 0.144. 0.0144. Okay, this means that in my K solubility product, the concentration of sulfate that needs to be in solution, remember that this equation looked like 2s squared times s, right? And this was equal to concentration of Ag plus squared times the concentration of the sulfate, 2 minus. If that is the final concentration of the sulfate when the second solid precipitates, what is going to happen to my initial equilibrium? That is the equivalent as adding more and more and more portion of the sulfate that needs to be available. For example, if we go back into our solubility equation, this would be simply adding that number into this section of our equation. So we know from the solubility product constant of barium sulfate that this is the concentration of barium 2 plus times the concentration of sulfate 2 minus. We know the value for the concentration of the sulfate, and we want to know the concentration of barium 2 plus times 0.0144 molar. Let me just verify that that was the correct value for S. Yes. So in this case, the value is going to be easy to calculate. Recall that KSP is equal to 1.07 times 10 to the minus 10. We have this common ion effect. So the concentration of barium 2 plus to keep this equilibrium will be 7.43 times 10 to the minus 10. Let's compare this result with the initial S that we found for barium sulfate. The S that we found for barium sulfate was 1.034 times 10 to the minus 5. So if we keep adding more and more sulfate, then due to the equilibrium, barium is going to precipitate even more, and we can end up with concentrations up to 7.43 times 10 to the minus 10 after the second solid has precipitated. And that would be all. You can also analyze this type of problem in the sense that you have an initial concentration of the sulfate. Okay, so for example, this would be in your ice table, In the case for the solid, it doesn't matter because that's a pure substance. At the beginning, let's assume that we don't have any of the barium. The concentration of the sulfate would be 0.144. The change would be plus X, or plus the solubility. And at the equilibrium, we would have X and 0.144 plus X. This is the common ion effect. In this case, we simply took a shortcut because we know that X, it is going to be much smaller, way much smaller than 0.144. If you want to use this method, and if in the case that you have some value of X that is closer to your initial concentration of one of the ions, then your solubility product constant you would need to solve this equation, which it is going to be a quadratic equation that depends on KSP. But as you saw from our previous result, this part is not necessary.